She tried to make me a costume. It reminded me of my high school plays, and she like sewed the sides together. It was so
All right.
like,
We're only missing Raquel, Arash, not that you're her keeper or anything, but you know if she's coming or?
I'm not entirely sure where she is.
Okay.
I can text her. There she is.
Here. All right, guys, everybody's here, including Dr. Desjardins. Hey, Stephen, first, do you go by Steve or Stephen? And secondly, is it Desjardins or Desjardins? Or what is it?
I usually go by Desjardins.
Desjardins.
Desjardins is closer to the French. Desjardins just gets me dirty low.
Right, right. Okay. Well, you're talking to Louisiana man, so we can do a little French imitation, some of us.
There you go.
Yeah. All right, everybody. I'm going to give us our quiz first. Okay. And go over to that. Here we go. So, quiz number 4. Ready?
no.
No, not ready?
Okay, ready.
It's only half a piece of paper. That's it. Don't have to be neat and tidy. Okay, ready? Ready? Here we go. Question number 1. A system's degrees of freedom was defined as its A, number of states, B, energy transfer potential, C, potential entropy rate, D, calculative efficiency. 2. One of the quantities we learned to calculate, A, free space, B, shells, C, KE, D, SYN minus 1. Question number 3, we read about a characteristic of a bowling ball that was A, flattened to the thickness of 1 atom, B, chilled to the temperature of absolute 0, C, heated, D, dropped from the Empire State Building, E, swallowed by a dinosaur. Number 4, a kind of entropy we did not read about today is A, Boltzmann, B, K entropy, C, entropy that accounts for differences between microstates and macrostates, D, a kind that was described using the table of ocean tides. Okay, question number 5. If we double the size of a checkerboard, by how many bits does the information needed to specify its state increase? A, 1, B, 2, C, 6, D, 12. Okay, that's it. Turn them over, please. Turn them over, please, and hand them in. Okay, put them out of the way. Got everybody? Okay, so let's go over those. Number 1, a system's degrees of freedom was defined as its A, number of states. That's right. One of the quantities we learned to calculate was C, KE, kinetic energy. We read about a characteristic of a bowling ball that was heated. That's right. Kind of entropy we didn't know. Sorry, yeah, right. Kind of entropy we did not read about today was D, right. No ocean tides thing. If we double the size of a checkerboard, by how many bits does the information needed to specify its state increase? 1. 1. Okay, good everybody. Way to go. you're doing the reading and you're doing okay on those. I understand you're going to miss one or two once in a while, even if you do the reading, but that's okay. That's why we curve it. So generally speaking, 80% of the quiz answers is an A, for sure, really. So good. Okay. Now let's go back to our Skype call, and there is Dr. Desjardins. That's right. And Steve, I think we can hear you. We got the lights right. And I'm going to put the laptop here so you can see us again, sort of, kind of. You don't get to see everybody this way. I'll tilt it a little bit more towards.
There they are. Okay.
Yeah, that's right. These are. We only accept really good-looking students here at Centenary, so they're all great.
Yeah, it's pretty good. No, that's good. That's good. That's good.
Is that good? Okay.
Not you guys.
Yeah, this person back there, I don't know about him.
That's right. Dariel and Diogene were missing a little bit. Okay. How about
Okay, we ready?
we are ready. Just Dariel and Diogene, just lean in there. We want you when you want to be seen. You too, Allison. Okay, Steve, take it away.
I'm all set?
Yep, you're all set. Oh,
Okay.
hold on, I got to increase the volume a little bit, but
Okay.
yeah, go ahead.
Great. Let me emphasize, folks, today, again, if you have questions while I'm talking, just get my attention somehow, so on and so forth, just because it's a lot easier that way if I can just answer questions as we're going. All right, today we're going to talk about entropy, energy, and information, three things that no one really understands. Over here. Okay. Energy is a very fundamental quantity in science. We define it as the ability to move things. That's the most fundamental way we can think about what energy is. Energy is what allows us to make things move. We often think of energy as coming as either in the form of kinetic energy, which is the energy of motion, the energy you have by virtue of your velocity, and potential energy, which is energy you have depending on where you are. Now, that's an odd concept, but we obviously know that if you walk, the higher you climb up a ladder, the more potential energy you have, and you know that it depends on your position in the vertical direction. Now, all systems are driven by energy, whether they're social, economic, physical, but it may be a little hard to identify exactly where the energy is. Nonetheless, it has to be a driving force in almost any system. Two words I want to introduce here are the idea of a sink and a source. For most systems, you're not separated from your surroundings. In other words, your energy is flowing in and out of your surroundings into your system, and back vice versa. So from the system's point of view, if energy is flowing in, we call that a source. In other words, a source of energy. And if energy is flowing out, we call it a sink. So again, think of my faucet model. The faucet itself would be a source of water. The sink would literally be the drain.
Okay, Steve, speaking of sinks, you're off to the right there. We only see half of your face. There you go.
How's that? Okay.
Yeah, you're right on the edge of the right. Yeah, there you go. Move it that way a little bit more.
Okay, how's that?
No, a little. There you go. Perfect.
Okay. I can't see myself. That's part of the problem. Go. Okay. Now, this is a mess. Let me apologize in advance for doing this to you. This is called the Liouville theorem. Notice it's not Louisville. It's Liouville. Liouville was a French mathematician, scientist. And I'm going to, despite the fact that this slide has got some written stuff on it, I'm going to go directly to the graph because I can talk about it. This is here for when you're looking later. So here's a graph.
Yeah.
So anyway, these two axes, x and y, we're assuming here that x and y are two state variables. so that the space defined by the x and y axis is actually phase space. Now, I want to emphasize that phase space can have any number of axes. Okay, so you could have a 2, 3, 4-dimensional phase space. If you have a billion particles and they're moving in 3 dimensions, you could have a 3 billion dimensional phase space with 3 billion axes. Now you can't picture that, but it's not that hard a mental extrapolation to realize that to be true. So what we're doing here is we take a set. Remember, every point in phase space is the state of the system. See, so a point, let's say right there, that point right there. Okay, whoops, rat. Did that wrong, okay? That point right there.
Hey Steve, sorry, you're being upstaged at this point by an animal. There's a dog that is standing in the doorway, looking pretty funny at us. But
Not the first time I've been upstaged by an animal.
Now I do have a question. Good, the dog left. He didn't pay tuition. Do you guys sort of understand what's going on here with those two squares? So you got the square and you got the rectangle. And the way I think of it, Steve, correct me if I'm wrong, I sort of think of it as the cube being the system at time 1 and the rectangle being the system at time 2, maybe. It has is changed, and
but remember, it's better to think of it this is not, these are many states of the system. In other words, you think a point in phase space is the state of the system. An area in phase space, the whole collection of states.
Right.
So these are all sorts of identical systems starting in slightly different conditions. And this is that same collection of systems later.
Right. But it could be a human being.
Sure.
Right.
This could be like a billion copies of you in all slightly different initial conditions, and then a certain time later, you take the same picture of that same billion copies of you and you're doing something else.
Oh, okay. I wasn't thinking.
That's why, see, this is a chunk of phase space. It's a piece of phase space. A state in phase space is just a point. A point would have the value of x and y. This has many values of x and y. So it's a lot of possible states of the system.
Possible states, right. Okay, I got it.
Right, so we're tracking a bunch of things at once. And the reason is this. As it changes, this initial square both moves and changes shape. Okay, so we're looking at kind of the global time evolution of the system. And what Liouville said was, if this was position and velocity, the traditional variables in physics, this volume would never change, this area here would never change its area. It could change its shape, but it could never change its area, okay, as time evolved. That was conservation of energy. So the area of this space goes as proportional to the energy of the system. So if the volume of this piece, I don't know, I keep disappearing. If the volume of this piece gets smaller with time, that means the system is what we call dissipated. Energy is flowing out of the system. If the volume were to get bigger, we would say the system is driven.
Yep.
In other words, energy is flowing into the system constantly. And if this area doesn't change, the system is conservative. It's also called Hamiltonian. Don't worry about that. Conservative means it conserves energy. Now everybody thinks, well, gee, energy is conserved, but remember, it's only the universe as a whole that conserves energy. You personally do not conserve energy. Okay, energy goes into your body in the form of air molecules and heat and food. It goes out of your body in the form of heat and waste and a bunch of other things. So energy constantly flows in and out of most systems. Now, here's how we want to think about this. If the system is expanding in area, or volume, as we like to call it, phase space volume, remember that thing could be an arbitrary dimension, so we normally say volume instead of area. We say the source is greater than the sink. In other words, more energy is flowing in than flowing out. These systems can only be modeled in the short term. The problem is, if the system is constantly increasing in energy, it's eventually going to break. And there's nothing you can do about it. Okay? So that's, you can model it in the short term, but not in the long term. If the system is isolated pretty well from the rest of the universe, That basically means no energy is flowing in and no energy is flowing out. That's a Hamiltonian or conservative system. Energy is conserved. This system has to be isolated from everything else. This is the system, believe it or not, that models most things. Okay? The energy flowing out, the energy can flow out faster than it flows in. Now you're saying, well, that leaves me with nothing, but it doesn't. Okay? This is just a capability. Think of it this way. If you've got water flowing into a sink, and it's going out the drain is big enough to take all the water out of the sink. The sink is never dry. Okay? There is always water flowing. The way you want to think about this is that this is a battery. You charge it up and it goes down and dies, and you charge it up again, it goes down and dies, and you charge it up again and goes down and dies. Now imagine if you had a battery that was constantly charging. Okay? So you would have a system where the energy was flowing out basically as fast as you put it in, but it was never, you still had something working. So the idea here is almost just like a water wheel. Okay, a water wheel's in a river. Okay? The energy, the water's going by and it's turning the wheel. Okay, and then it continues to move on. That system is dissipating because the river were to stop, so would the wheel.
Sorry, Steve, I'm just trying to, we're getting distracted by my little, there we go. My alerts about
Right.
Dropbox and stuff like that. If there's anything way to do that. There we go. Okay.
Got it?
Yep.
So here's the key conclusion of this. Most of our realistic models will be dissipated, which means any system that is a really real system, physical or social, the phase space volume is eventually going to go to zero. Now that sounds like an incredibly dull thing. The picture in your head is that box is going to crush itself down to a dot. And indeed, it can do that. That would be a fixed point. All right, that's a simple evolution of the system. So no matter where you start, eventually you're going to do this with one thing. However, that's not the only possibility, and I'm going to explain why. You can get a number of shapes that have no volume. And here's why. It's a simple system. Suppose your phase space is three-dimensional. Okay, phase space volume is therefore traditional volume. What's the volume of a flat surface?
Zero?
Right. In other words, if you have a dimensionality less than the phase space you're in, you have no volume. So if you're in an 8-dimensional phase space, a 7-dimensional thing has no volume in that 8-dimensional space. These figures that you form in the long term are called attractors, because, if you will, the system is sucked into this shape. I'm going to give you the pictures now. You've seen this picture before.
Yeah.
If you really lose, if you crush down to a dimension, okay, this is for a 3-dimensional phase space, then you end up with a fixed point. This means you go to the state and you stay there. This is unchanging. Every state variable has a constant value. If you're going to go periodic, you can have a limit cycle. Limit cycles are closed loops in phase space. Now I've drawn a nice clean one here, but it doesn't have to be that clean. It could be a lot messier as long as it comes back. And the idea is you start here, you move around space, and you eventually return to the same state. Since the system is deterministic, once you return to the same state, you've got to do the same damn thing all over again. So you repeat yourself. The torus just happens when you have more than one frequency present. So this can live in 2 dimensions, and you'd have one period in this direction and one period in that direction. If you had a phase space that was a billion dimensional, you could have this stupidly high dimensional torus describing your behavior. Finally, you get these things. These would have been, again, pre-1960, no one thought these existed. These are called strange attractors. Strange attractors are the attractors displaying chaotic motion with the chaotic attractors. They're kind of like the limit cycles, except they keep missing. They can never quite repeat themselves. They're like cycles that got really messy for some reason.
But Steve, it looks like that would, once you go through both sort of sides of the strange attractor, you might repeat yourself, right? But is it moving in other ways too?
And that's right there is the reason why. This thing can spiral around, but then it literally jumps directly to the other disk. And it can jump right in between these. Remember, these trajectories have no width. So no matter how many times you spin around, there's always a bunch of spaces you haven't been, and this one will jump right into the middle and it'll spin around in between them. Okay? This is a very...
Right, okay, I think I get it. Now is one way of thinking about it just the way, like looking at the limit cycle, about how, you know, the winter of our seasons, right? We think that it's sort of like, oh, it's the same seasons all the time. We always have winter, we always have summer. But if you look at climate change and how it's changing things, that's another sort of variable that makes it a little bit different each year, and you won't repeat yourself exactly. And there's a lot of actually there's a lot of states that go into that.
Mm-hmm. Think of it this way: if this were just a cycle, it would be a circle like this. Okay? What this particular shape is, you've basically got two circles, and you can jump back and forth from one to the other. Now notice the interesting part of this. Just because I'm never repeating myself doesn't mean I need an infinite amount of space to move around in. This thing exists in a very well-defined space. You never go higher than this, or wider than that, or wider than that. Those state variables are always perfectly well-defined. They just never repeat. And the reason they never have to repeat is because, remember, these are real numbers. Real numbers, there's an infinite number of them. So you can constantly jump back and forth between real numbers. And that's what's happening with the strange attractor. These things have all sorts of shapes. I want to emphasize, this is one particular strange attractor, one of the first ones discovered due to Lorentz. There's another one, for example, if you go onto the internet and type in strange attractor to Google, you'll find all sorts of marvelous shapes. These things actually get pretty astonishingly complicated.
Yeah, hold on, we got another question. Maddie?
Yep.
How does the strange attractor relate to the dissipative system? Like, I missed
To the
connection.
To the dissipative system. How does the strange attractor relate to the dissipative system?
Boy, that's a great question. And here's why it's a great question. This is three-dimensional space, right? So it's got to be less than three-dimensional. Well, that's clearly, a fixed point is what we call a zero-dimensional object. It only has one position. It has no extent in space in any direction. A limit cycle is a one-dimensional object. It curves through the three-dimensional space, but you could give me my position on the cycle by only giving me one coordinate. The torus is a two-dimensional object. Remember, we're talking about the surface. This is a hollow thing. It doesn't have anything in it. So that to tell me where I am on the torus, you need to give me two coordinates. Okay? So here's the strange attractor. It's got to have less than three dimensions because it's dissipative. However, and it's hard to see this, like I can't spin it, but if you took right here, there's no way those two plates could be completely flat. I mean, the plates are flat, but this crossover area has to jump between the two, and you could never compress that thing flat without those lines crossing. And if those lines hit each other, then you have a problem because it's a deterministic system. Once those lines actually cross, once you come to the same state, you can't cross in a different direction. So we have the weird conclusion that this thing must be less than three-dimensional, but greater than two. Okay, does that bother your head?
Yeah, that bothers the head a little bit.
Okay, this is why you often hear this field when it's discussed, is often they talk about chaos and fractals. Okay, a fractal is a kind of geometric object that has a non-integer dimensionality. This thing is 2.061 dimensional. Now, yeah, I know, I can see people grabbing their heads. Oh my God, why did you do this? I'm not going to go into any detail about that because we just don't have enough time. Fractals are a fascinating thing. They were discovered in the 60s and 70s. the fact that dimensionality didn't have to be as simple as we thought it was. It's been a hugely useful concept, especially in biology. Okay, biology has found your lungs are fractal, your brain is fractal, trees are fractal, and the trick of them is, here's one way to think about what fractal does. If you have any kind of a shape, you all have calculus, right? You zoom in enough, okay, and let's say you have a curve of some kind. You zoom in enough, and the curve looks straight. If you zoom into a really, really tiny bit of curve, a fractal never does that. It's got bumps and wiggles at all length scales. You zoom in, it's got bumps and wiggles. You zoom in, it's got bumps and wiggles. You zoom in, it's got bumps and wiggles. It is, to make the mathematicians truly cringe, it is nowhere differentiable. In other words, you can never take the derivative of a fractal curve because it's never, ever, ever, ever flat. And,
by the way, Steve, there's first of all, I don't think everybody here has necessarily had calculus. But secondly,
okay.
Fractals, there's a demonstration of fractals, y'all, in the in Turner Art Center. There's lots of different artistic depictions of fractals.
Oh, fractals are lovely. As a matter of fact, fractals look realistic because nature is fractal. Nature is very fractal. You're saying, well, gee, but think about it for a second. If you think of normal Euclidean geometry that you've learned, spheres and planes and lines, nothing is a perfect sphere or a perfect line or a perfect plane. Fractals look more realistic. They have a lot more structure. They have a lot more complexity to them as geometric figures, and they look a lot more like real objects. Fractal algorithms, as a matter of fact, are used to generate computer-generated animation. So in other words, if you want to make mountains and trees in a cartoon or something, or generate a background, they use fractal algorithms to do that. They look far more realistic.
And
now, we don't have to know that to do this.
Sorry, but by the way, your upper Skype window, the one you're moving around, is sort of covering up the word. Maybe you can move that up to the top left or right or something.
Oh, it just says deterministic chaos.
Yeah, okay, good. And also, just on this, isn't it sort of true that one of the reasons we're talking about this, or this is important, is because nothing ever really repeats itself perfectly?
Right. That's exactly what happens with deterministic chaos. You never repeat yourself.
Right.
Think of it this way. If you want to have a complex system, and if you're going to describe it geometrically, the geometric figure you're going to have to use is going to have to reflect that complexity. Well, regular geometric objects like a torus just only so complex. This is a much more complex object. And it turns out this particular strange attractor was used to predict the behavior of the weather. Okay, this actually is I forget, the height is like the temperature difference. The which wing you're on is whether the wind is blowing east or west, and the speed is how fast you're going around. So what happens is the wind's cheerfully blowing, and all of a sudden it jumps to the other wing, the little butterfly here, and it's spinning in the wind blowing the other direction. That's exactly how the wind behaves. Okay, it blows in one direction, it blows in the other direction, it changes direction randomly, seemingly randomly. Well, this is actually an object that encapsulates that behavior. What's really interesting is Lorentz discovered this in 1962. His computers were, I can't emphasize how stupidly simplistic they are by our standards. He could never have calculated the shape of that figure. He was able to calculate one line like that. But this is why Lorentz gets the big bucks in the history of science. He looked at it, thought about the equations, and said, this is an aperiodic flow. That thing's never going to repeat. It took 10 years before anybody could actually had enough computing power to draw the Lorentz attractor. So it was a great example of just this person looking at something and visualizing something horribly complicated that he could never even draw. Okay. Let me zoom on here now. Let me go back to the start before I go there. Okay, Now, why did I just do all this to you? We had to end our discussion of dynamics. Remember how this started? We started by talking how like a few particles move through space according to Newton's laws. Then we talked about that population model. We saw that even something with very few degrees of freedom, with very few state variables, could become arbitrarily complicated by going into chaos. What I've showed you now is what this chaos looks like in phase space. Okay, this is simply, literally, that you get a strange attractor. You get some incredibly, you look at this thing, you see this thing, right? It's obviously not random. This is not a random collection of points. That thing has a definite shape.
Right.
Okay, but it's just a complicated shape. And that's what, again, mathematicians basically discovered in the 20th century with these incredibly complicated geometric objects and how to draw them. Now, any questions before I?
Well, I just want to emphasize to everybody and sort of check with you. I mean that idea that in a strange attractor, that sort of system, it never repeats itself. So
no.
a lot of people, their vision of the fixed point sort of thing or the limit cycle thing is that the universe or seasons sort of work like that. So the universe collapses in on one point and then it explodes and then it will collapse in again and it'll explode. And so things will repeat themselves, but they won't actually be repeating themselves.
Well, the two things there. One, and I
know I brought up the universe. Sorry.
No, cosmology is, a subject we're still learning a lot about because we can't look to everything. The current predictions is the universe won't recollapse. The rate of measurement of the expansion of the universe turns out to be actually accelerating, not decelerating.
Right, yeah.
So who knows what's going to happen? But the other, if you will, point of this is that we don't see things repeat. And we always thought it was just because we were seeing errors. Notice how insidious this is. If you ever saw your system in your lab repeat, you'd say, oh, it was just because I didn't measure it well enough, or it was somebody was causing vibrations or something in the room. It's very easy, in other words, to see something move randomly and think that's just a mistake. In other words, it was just an outside influence. This is why it took a long time for us in the 20th century to be able to measure things precisely enough. Saying, no, this system is isolated enough. It's not getting noise from the outside. It really is generating its own apparent randomness internally. That was really hard to do if you don't know to look for it. Mm-hmm. Especially, for pendulums, for example. If you see it for a pendulum, then you know it probably really exists. Because that's a very precise system you can define very carefully. No one's surprised the economy shows unpredictable trends. But when a pendulum does it, that's when we all get excited. Okay. Now, all of this, as I said, is the mechanical approach to life. The mechanical approach to life means, I know where I am now, I'm going to predict where I'm going to be next. What if our system has lots of pieces to it? Okay, lots of pieces to it, like matter has lots of atoms. Then we've had to move on to something else, something called thermodynamics. And I gave you a nice little summary here of things you could read. And let me emphasize, this is we're cheerfully working our way through every major field of physics. And that's, so if you feel confused, that was an excellent choice on your part. This is ludicrously messy. But here's what happened. Thermodynamics simply means, this is the subject of trying to explain how macroscopic bodies, in terms of particles that make them up. In other words, I know that, any, like a little cannonball or something, right, is composed of a lot of atoms. Yet, I think of the cannonball as an object with a certain set of properties. How can I explain the properties of the cannonball in terms of the properties of the particles that make it up? Okay? That's the way we think about it. But we sort of see different levels of reality. When you look at a table, do you see an object or do you see a collection of atoms? Okay, both are legitimate viewpoints from the modern perspective. I want to emphasize that thermodynamics is a incredibly practical subject. It came about during the Industrial Revolution. It came about primarily as a way to improve the performance of the engine. So let's take a key here, okay? In thermodynamics, we think of it this way. For macroscopic systems, there are two ways to transfer energy from one body to another, called heat and work. All right, mathematically, here's what it looks like, but who cares? Let's go to the picture, okay? And despite the fact that Lauren said bowling balls, I have cannonballs here.
Oh yeah, sorry about that. Sorry about that.
All right. Here's the trick. See how, if you're a mechanical system, the only thing you can do to a particle is to move it. When you move a particle, it's called work. Now, if you have a body like a cannonball that's made up of many particles, and you move every particle in exactly the same way, that is also called work. In other words, by moving all the particles in exactly the same direction, the body itself moves in that direction. There was no problem with that. Newton understood this perfectly. But what's the one thing they always tell you in physics class when you move something? Neglect what? Friction. Okay, you always have to neglect friction. Okay, why do they tell you that? Here's what happens. Suppose I move all the particles, but now I move them in different directions. The particles are all moving. I've done work on every single tiny particle. But the body itself doesn't go anywhere. How do I perceive that energy being transferred? Whereas I would perceive this energy as being an increase in the velocity of the body, I would observe this as a change in temperature. Okay, this would start moving and go faster. This would get hotter. And that took a long time to understand. Realize that it wasn't until the late 19th century that we really acknowledged that things were made of atoms. The only way to understand heat as a way to transfer energy, and we know you can transfer energy by heat, you do it every day, heat things up. What you have to understand is that it doesn't move the body in a visible way like you see in mechanics. What it does is it moves the particles that make up the body in a perfectly good way, but the overall thing you see in your head is the body itself getting hotter. Now notice what happens, by the way, if you take water, if you heat it up enough, it turns into a gas. Okay, that means that you've given these little particles so much energy, they're able to move away from each other. So this no longer is restricted to be a solid or a liquid object, it actually starts to fly apart. So this is what the first law of thermodynamics had to acknowledge. There were two ways of transferring energy to a macroscopic body, a many-body object. One, you move it all in the same direction, or two, you move them in different directions. Work is an orderly transfer of energy. Heat is a disorderly transfer of energy. Okay, and that took a long time to work that one out. All right, this is normally attributed to a guy named Joule. I'm sure you've heard of the unit of energy called Joule. He was the one that figured this out. Interestingly enough, what he did for a living for a while was he made cannons.
No, I thought you were going to say he was a jeweler. Come on, man.
No. He was a cannon maker. And what he realized, though, is he was boring the bore in a cannon with a drill. He was doing work, obviously, but of course, we all know what happens when you do that. The metal itself gets hot. And he was the first person to make that connection that heat is actually some kind of energy transfer. All right, he managed to work out the details of that.
And if I can, Steve, I mean, when you introduce heat onto a lot of different stuff, right, it sort of disorganizes it. We're looking at those two different cannonballs there, and so
right.
it makes the firmness, the integrity of the shape less, less firm.
Sure.
Yeah.
If you take the cannon, what happens is, like with a really piece of metal, there are forces holding the particles together, but the hotter it gets, the faster they vibrate back and forth. If it gets hot enough, they start to move around each other, and that's the cannonball melting. If you heat it up even more, eventually these particles have enough energy to go flying off in all different directions. That's when it becomes a gas. Now,
I just want to say, by the way, Steve, I just want to say to them, to the class, that we're going to come back to heat and work and the difference between heat and work throughout, I think, the course. I think they're useful concepts. When you think about communication, when you think about social systems, and so I was writing down in my notes about one of the phenomena that's happened in a political system is how if there's not sort of heat coming at you, can you go back to that? Well, no, you don't have to go back. But if there's sort of unfocused energy, which is not work but heat in a sense, unfocused energy coming at a body, it'll sort of disintegrate and lose its integrity. It'll start infighting. Things will sort of break up. And whereas if there's focused energy at it, it will cohere. And that happens a lot with social organizations. So you feel camaraderie before you're about to go on stage with your fellow cast members in a production, or with your teammates, or with your classmates before a standardized exam or something like that. So there's ways in which we organize ourselves to all go in the same direction when there's work to be done. But when it's not clear what the job is or something like that, we're more likely to be, to partisan bicker and so on. Like after the Soviet Union's fall, there's a lot of partisan bickering ever since. And anyway, so we're going to come back to this sort of phenomenon. Thanks, Steve, for letting me intrude.
Okay. Yeah, well, I'll move on to this next piece. This is just, again, an re-emphasis of this set of slides, that again, we have a system and the surroundings, as we did with mechanics. The only thing is now we don't try to separate, but we allow energy to be exchanged between the system and the surroundings. Energy can be exchanged in the form of heat. Obviously, heat can flow out, heat can flow in. The other possibility is energy can be exchanged in the form of work. The system can do work on the surroundings, or the surroundings can do work on the system. So now we're acknowledging that things flow back and forth. Okay, and again, it's just saying a little more here. Now, here's a significant limitation of the first law of thermodynamics. But notice what the first law said. It said if you change the energy of the system, those changes had to occur by either heat or work. You had to move it in some way, or you had to change the temperature. Well, look what happens here. This is the most obvious thing in the world. If I take two things, thingy one, thingy two, we call them bodies, because we call them thingies, the NSF won't give us any money. So, this is the hot body. Okay, is it 100 Celsius? Is it the cold body? Is it 0 Celsius? I put these two things in contact with each other. What happens? The hot body gets colder. The cold body gets hotter. Heat flows, energy flows in the form of heat from the hot body to the cold body, and it will continue to flow as long as the temperature of the hot body is greater than the temperature of the cold body. Now, this is a fairly obvious thing, okay? Except you have to realize something. The first law of thermodynamics can't explain this, because the two bodies together always have the same amount of energy. So why would it prefer any one state over another? Why would the energy flow from the cold body to the hot body? That also conserves energy. It's lower heat. So we knew that conservation of energy, in the form of heat and work at least, could never explain everything we were observing about nature. We observe some processes go, heat flows from hot to cold, and some processes don't go. You don't go from cold to hot. Okay, so what was going on there? Well, obviously, we did the second law of thermodynamics. Okay, the second law, if you will, the first law helped us understand something we saw every day. The second law, though, was really the profound insight into the problem. And what it realized was, since energy is conserved, it can never tell us which direction the system is going to go in, because the energy never changes. It's a constant. A constant can't tell you which way you're going. Fundamentally, if you want to know which way a process goes, you need a system that changes either up or down. Say, oh, it goes up in this direction, that's the way the system will go. That property is called entropy. Now, entropy is often interpreted as, and we're going to talk a lot more, the first interpretation is it is disorder. Systems tend to flow from a state of order to a state of disorder. Or another way to look at it is the energy becomes more dispersed. That is the normal way you talk about entropy. But I want to emphasize it's an incredibly simplistic way to talk about it. Yes, it's not wrong, but it hides a lot of important features. This is the key thing the second law of thermodynamics says. It says the total entropy of the system and surroundings together must increase for any spontaneous process. So the system changes in entropy, the surroundings change in entropy. If you add those two changes together, those changes have to be positive. If it's negative, that process doesn't happen. So you'd never see entropy drop if you look at the total system. Now, of course, the obvious question coming through most people's minds is, what the hell is entropy? Right? So how do we want to think about it? Okay. Now, not a devil, but a device, sorry. Okay, let's take a look at an engine. Okay, because that's what started the second law. That's what started the whole thermodynamics thing. Human beings discovered engines, the steam engine. What does an engine do? An engine is a device that converts heat into work. You make a fire, okay, you boil the water, and you get work out of it. So in other words, you're taking energy transferred as heat, changing it into energy transferred as work. Now, what's the most obvious thing in the world you want to do? You want to make that engine as efficient as possible. An engine that was 100% efficient would mean that if I put in 200 joules of heat, I would get out 200 joules of work. Another way of looking at it is, I think of those two cannonballs, a perfect engine could totally reach in somehow and align those particles moving in different directions to all go in the same direction.
You moved out of the picture, Steve. Sorry, that was a great gestural moment. You moved out of the picture a little bit.
Sorry. All right,
Yeah,
let me go
back
back
to
though to a few. I should just probably go on. There we go. So in other words, imagine the perfect engine would be a device that could somehow organize all those particles to move in the same direction. Now imagine how that would work, okay? You have to actually take this, so this particle, you heat it up, so now the particles are moving really fast but in different directions, and you do something to make them all go in the same direction. Notice that you haven't changed the energy any. They're all moving, all the particles are moving at the same speed they always did, they're just now moving in the same direction. So somehow you could take this thing, organize the particles, and it took off. Okay?
Yeah,
So
Steve, I'm sorry, I didn't mean that you should go back in that picture. I just meant that you were yourself moving out of our picture so we couldn't see you.
Right.
Sorry.
So but I wanted to go back to that
Okay,
picture,
okay.
so you could see this. Okay, now, so let's look at what an engine looks like, okay? This is a little more complicated than it has to be, but nonetheless, we'll look at it. Here's, we've got a gas in here. I said it's an ideal gas, who cares? It's gas, all right? I've got a hot thing and a cold thing, all right? I have the hot